University. And today we're going to do, I'm not going to present, you actually going to do that for me. We'll see that how in the next slides. But we're going to talk about LCA, so something a bit different from what you've been listening to in the past few days. But I think it quite nicely linked to what Esteban was presenting earlier and how an LCA tool can help in addressing, for example, David's question on Esteban talk. So could you please get your phone and connect to menti.com? Yeah, either use the code or the QR code. Oh, no. So, few questions just to break the ice and gather some understanding of your knowledge so far. So, are you enjoying the training school so far? Well, you are halfway through.
I'm still waiting for
The code is still on the top. Obviously, there is no negative answer. So, next question. Could you please explain your research project using only 3 words? And that is needed for later. That's tough, isn't it? So 3 keywords to explain your projects. So self-filling concrete, sustainability, durability, LCA, I might know who that is. Cyclic, impact and thermal, concrete durability, extreme condition, self-filling testing efficiency, mixed design concrete, numerical simulation, corrosion, and I think we can scroll down. Commercialization of self-filling, real scale service life, modeling. I don't know if anyone is contributing from the online audience. Corrosion of reinforcing self-filling concrete, thank you very much. Next one. What is the first thing it comes to your mind when you read the word sustainability? The first thing, it doesn't need to be linked to the training school, to your research. It can be anything. You can think of sustainability of recycled plastic bottle. What is the first thing? Green, environment, durable, durability, global change, yeah, nature, environment, world, urgent, reuse, reduced emissions. What's new? Obviously, the biggest word is the one that's been typed the most. Live, work better than nice. Thank you. So now be honest, there is no marking, there is no judgment on that. How much do you know about life cycle assessment? We have an expert, apparently. Okay, well, at least there is no one on the left-hand side of the screen. That's reassuring, that's a start. And what do you think LCA is used for? Prediction? Yeah, to convince people, yeah. Well done. To address certain advantages, sustainability, cost analysis. We'll see that in a minute what cost means. Prediction business models. Davide's PhD. Quantification, assessing the impact on the environment over a lifetime, prediction. Yeah, well done. Thank you. Now back to our presentation. So, a couple of slides with data that you already know very much, so I'm not going to present the same data about how polluting concrete is, but just to, I don't know if you ever come across of this article was in the BBC last year. Concrete is the most destructive materials on earth. So in terms of publicity, we all work with concrete. In terms of publicity, if that article is read by someone that doesn't know anything about concrete, so we're talking about the general public, that's what they come across with. Why? Because that's the production of concrete we are at the minute, whether it's the latest data from 2020, 4.1 billion of ton. And obviously we know the cement production contributes to approximately 8% of the anthropogenic CO2 emission. So there is a need which is called the net zero agenda, carbon agenda, which we all know about, I hope. But what's interesting is this change in policy and net zero and carbon agenda is not only within the concrete industry, but there are also some other industries probably we didn't think of that actually are thinking of switching into carbon negative. And companies like Sky News, Microsoft as well. So Microsoft, we can understand why, but why Sky News wants to be carbon negative? What is that they actually produce in terms of CO2 emission? And obviously to assess in each company, to assess their carbon emission, they use some tools. And one of the most used tools is actually the life cycle assessment. So before we dive into the life cycle assessments, just to recap some of the principles in terms of sustainability, one of the most known principles is the 4 Rs, reduce, reuse, recycle, and restore. So if we think about that principle within the construction industry, that means, for example, demolition versus repair, assessing whether do we need to demolish a structure? Can we do something with the structure? Can it still be repaired and be used for something else? Or indeed reuse the demolition waste and change the perspective from EOL to BOL, end of life to beginning of life. So using something that is discarded as a material that actually can be used to start something new, something different. Or looking at completely different materials. Self-filling materials is one of them. Looking at agricultural waste, alkali activity materials as a pozzolanic materials. And finally, looking at durability, which is what the previous discussion I will carry over during the talk about assessing the durability, how this is important. I remember I really like the triangle that Esteban pointed out, where durability is the least aspect that you are able to demonstrate, convince, or to use in commercializing your ideas. So, building cycle. This is not something new to you, but I thought I'd put there just to start talking about life cycle assessment. So, in a life cycle assessment, what we need to picture, if we go a product, a material, a process of service, we need to think about starting with the extraction of the raw material, assessing what materials we need, the manufacturing of those materials, their construction, operation and maintenance, and then the end of life, demolition, and what do we do with these materials? After they are demolished, we store them safely, we dispose them into landfill, or we reuse them. There is a really nice, useful book. It's called Life Cycle Assessment in the Built Environment from Crawford, and that has been my Bible for quite a while. But what is interesting, and that's why I mentioned Sky News earlier, a life cycle assessment tool is not only for a pothole, it's not only for self-healing concretes, but life cycle assessment can be used also to assess the environmental impacts of a service that we offer, or also the environmental impacts of a process. So when we think about life cycle assessment, it's used for product, process, and services. Embedding life cycle assessment means implementing some of the strategies, such as reuse, design for disassembly, design for recyclability, design for durability. They all have some environmental benefits, which are preservation of natural resources, reducing waste production, minimization of land use, and so on. So, what is life cycle assessment? I've taken the definition of that directly from the regulation, which is the ISO 14040-2006, and is a compilation and evaluation of inputs, outputs, and potential environmental impacts of a product system through its life cycle. Also, what the regulation says is the life cycle can assist in identifying opportunities to improve your environmental performance. And that's really important because usually what we do with our research, and academically speaking, what we do is we got this fantastic idea, we have this new self-healing concrete, this technology, we do all the experiment in the lab, and then the last chapter of our paper, the last chapter of our PhD, is a life cycle assessment. Let's dedicate a couple of weeks and let's build a life cycle assessment. And then we end up with some rubbish data because we didn't think that some of the technology that we were using are actually very polluting, emitting quite lots of environmental emissions. So what the life cycle assessment should be used for, you should start your research with a life cycle assessment, because then you can identify what process in the production of your concrete are actually releasing environmental emissions, and then rethink of that process and recalculate your life cycle assessment. And also can be used for informing decision makers. And that's a point, again, that I take over from last talk. For example, on self-healing concretes, or if I today want to develop a new construction material, there won't be any legislation, there won't be any regulation, which I can go to my designer and say, or to my client and say, use these concretes, I can tell you, I tried in the lab, it's really good. And then say, where is your proof, where is your evidence? You don't have any regulation to prove that. That's what durability testing comes into hand and help you producing those data, simulate your service life up to 100 years, and then you can go back to the policymaker and say, we got the data, now you can trust that. So, there will be a test at the end of the lecture, so make your notes. The four main categories, the four main elements of an LCA, and as stated in the international standards, those are compulsory. You need to have goal and scope definition, inventory analysis, impact assessment, and interpretation. Let's quickly analyze the four of that. So, goal and scope. We need to understand what is it that we are doing with our LCA. Are we doing the LCA calculation to actually verify the process that we are doing, or are we doing to convince our audience? And also, who is your audience? Who's going to buy? Is the general public? Is a government body? And then the scope. And this is something really tricky, and I'll show you in a minute why. We need to compare like for like. So when we do a life cycle assessment, choosing the functional unit, it's really important. And the functional unit is not necessarily a beam, so the production of one beam of concrete. It's not necessarily a 1 cubic meter of concrete. A couple of examples to let you understand what a functional unit is. I want to do a life cycle assessment of a conventional car, like a petrol car, and an electric car. What will be my functional unit? I'm asking the audience. There is no wrong, well, there is a wrong answer, but don't be shy. So, life cycle assessment to compare a petrol or a diesel car with an electric car. Okay? If I compare the two of them, if I break down all the materials, obviously the interior will be the same, but the engine is different. So my functional unit cannot be petrol, my functional unit cannot be the engine, because that will be different. The energy, no, again, because the energy will be from two different sources. One is electric, will be impossible to compare. Kilometers, thank you, Stepan. If I want to compare an electric car, a life cycle assessment of electric car, and a life cycle assessment of a petrol car, I will be comparing the mileage, the kilometers, how many kilometers I can make with an electric car and with a petrol car. So that will be my functional unit. If I'm doing self-filling concrete, doing just or simply a 1 cubic meter of concrete and comparing, probably that's not the best. It might be the case for some of the self-filling technologies, but might not be the case. For example, if I want to do a life cycle assessment of a structure built with conventional concrete and one with 3D printed concrete, what will be my functional unit? I can't compare cubic meter for cubic meter because the efficiency of the 3D printing is the actual shape. So comparing 1 cubic meter for 1 cubic volume per volume won't be the smartest choice. So I hope you have a feeling of what the functional unit is. And obviously we need also to define in our goal and scope the system boundaries, which we'll see in a minute what they are. But we need to define where do we start our analysis and where do we finish the analysis. And the assumptions, which are, as per any scientific methodology, assumptions are vital. So, again, as for the international standards, this is a snapshot of a typical life cycle assessment for concrete production, and you see 3 different terms which you might have heard from past discussion: cradle to gate, cradle to grave, and cradle to cradle analysis. So we are defining the system boundary. That means that when I enter on my life cycle assessment software, the raw material for me will be cement, Portland cement clinker. In the LCA software, in the LCA database, you find values, emission for those materials, but this is not a virgin material, the primary source, because I know that from Portland cement, I can go back and get limestone, sandstone, and all the processes. Yeah, and then I can go even farther back from limestone extraction. So defining the boundaries, it means defining where I start and where I finish my life cycle assessment. It can't go forever. Cradle to gate analysis is where I start from where my boundary is, and I follow all the operation, construction, manufacturing, operation, transportation until the construction point. After the construction point, that's another type of analysis, which is called cradle to grave, where I actually follow through the process of construction, the usage of the structure. It might be a building, might be a bridge, And then I follow also the end of life, the demolition of the structure and the transportation into landfill. In a cradle-to-cradle analysis, which is what the circular economy principle lays in, is where we add as a final step the production of waste and the reusage of the demolished, the end of life, back into the circle. So if I'm demolishing a building and I want to do a cradle-to-cradle analysis, then I will need to take into account what is going to happen to all this demolished steel, concrete, transportation to a factory, crash them into construction demolition waste, and then ready to be manufactured and to be incorporated in another design. So that's a cradle-to-cradle analysis. Really difficult to do, but very powerful instrument, and especially for marketing purposes. Life cycle inventory is a data collection and a flow diagram. So you break down all the processes of your projects, you try to identify input and outputs, and then you draw a flow diagram. It seems very abstract, but it will make sense now. For example, transportation of concrete as a process. My input will be cement, sand, aggregate, water, the energy for mixing, and the transportation factor. The output will be the final product, transported concrete. Secondary outputs are any waste. Oops. Flow diagram of, again, life cycle assessment of Portland cement. So we started from quarrying the raw materials, so fair to say that this is a very thorough cradle to gate analysis. So they started from quarrying the raw materials, meaning extracting, excavating and crushing all the aggregates. And you can see all the input and output as emission and energy and heat. And then we follow through the processing of raw materials, preparation, dry mix, and then the clinkering process until packaging and shipping. One thing I wanted to also make you aware that when you do a life cycle assessment based on data from the lab, might really differ from what you actually get on a factory scale. If you think of a life cycle assessment of concrete mixing using the mixer that you have in the lab, which is a 350 watts mixer, a standard mixer, it might not be the same emission that you would have for a lorry mixer. The same when you produce your concrete in the lab, the scale effect, when you scale everything up, might actually play quite a significant value. Finally, the last two steps are impact assessment and interpretation. Impact assessments are the one with the noted with the asterisk is the compulsory according to the ISO standards. We need to choose the impact methods. Usually it's the recipe or the ILCD, which has impact methods produced by the European Commission. Weighting and normalization. It means based on the factor, you will see in a minute, based on the environmental factors, which one we give more weight to and how do we normalize? Do we normalize by population? Do we normalize by impact to the environment? And then we choose the categories which are indicators and factors, the impact categories that we want to look at. A snapshot from another paper, life cycle assessment 3D printed geopolymer concrete. And you can see that on a very honest research, they show the difference between the environmental impacts, and they chose here to represent as a carbon dioxide equivalent. So they show all the gases, all the emission, sulfur, nitrogen, and the minor one as an equivalent to carbon dioxide. And they show the difference between a 3D printed geopolymer concrete and an ordinary concrete panel, where you can see the geopolymer one has a higher impact. And then to actually understand why that has a higher impact, in the impact assessment you can see the contribution of each single process or material. For example, the green one is the transport. And when you deal with an LCA, I'll show you even on my case study, the transport is actually the one that is the most dreadful to get rid of. Whether in the other one, in the ordinary concrete panel, the elements, the compound that has the highest impact is the cement production. And then you can look at other environmental impact category on the graph on the right-hand side, where you can look at each single scenarios. You have your own calculation, your different scenarios, sensitivity analysis, that's what we call. And you can understand what is the process that will impact the most and what category impact the most. Finally, the interpretation. Sometimes this is the phase of LCA, especially people that just started with LCA, they neglect or they think it's not relevant, but actually this is what makes the LCA relevant, because it's in the interpretation stage where you give recommendation, where you understand what is in your LCA, what are the processes that needs to be improved to enhance or to lower the emission, and that's where you do a sensitivity analysis. For example, in the previous case, we've seen that the transportation, the green one, is quite high, as well as the electricity consumption in the 3D printed concrete. And that can, is that the electricity? No, it's the silicate, sorry. But the transportation, is there a way through the sensitivity analysis that we can improve our supply chain to reduce the transportation? Do I really need to get my sand and my gravel from Aberdeen? Can I improve that? So that's why a life cycle assessment is useful, because it comes down to those sort of questions and challenges and highlighting some of the issues. And obviously, as I said at the very beginning, life cycle assessment is not something that you do as a cherry on the cake in your work, but it's something that is iterative. You do once, you understand what the issues are, you solve those issues either in the lab or in your supply chain, and then you go back and repeat the life cycle assessment. So I'll give you an example of a life cycle assessment that we did on a piece of our work. This is a self-filling concrete using shape memory polymers. So tiny fibers knotted and mixed in mortar in this case, and no, concrete, I think, yeah, concrete, sorry. And you can see the effect of these shape memory polymers. They are able to fully close those cracks. So what we did was, first of all, comparing the production of 1 cubic meter of concrete, conventional concrete, and 1 cubic meter of KSMP, knotted shape memory polymer fiber concrete. So we put a lot of assumption there because we were interested in other components, which you will see. So we broke down the two scenarios. So conventional concrete, what we have, The first unit is concrete production. My input were water, sand, aggregates, and cement. Output was concrete. Second process was the transportation of this concrete. So my input was the concrete from the unit before and the transportation. Output, the transported concrete. Easy peasy. Let's move on the self-healing concrete. We need to start from the shape memory polymers. So in these shape memory polymers, we buy in a form of PET granulates. How they are made, those PET granulates, I don't know. I decided to put my system boundaries there. So I acquire my PET granulates. I include the transportation. My output is the transported PET granulates. Then the transported PET granulates, they go into another process with the melt extrusion twice to give the shape memory effect, and the knotting. The outputs are the fibers. Then the fibers are then transported from wherever they are made, Bradford in our case, to Cardiff. And then the fiber are mixed with the cement, water, sand, aggregates. I included also the mixing energy. And the output is the KSMP concrete. And then the KSMP concrete is transported, so I added the transport, and the output will be the transported KSMP concrete. So this is the model graph that comes from the software that we use, LCA, where you can see exactly what I've done on Excel. The inputs, the outputs, some of the inputs are already parts. You gather those information from the database that we use. In this case, we use EcoInvent. And then we did the impact assessment, which to do that, it takes only a couple of minutes on the software. But to gather all the information prior to the lifecycle inventory, that's what it takes the majority of your time and patience. So let's look at the global warming parameter, so the kilogram of CO2 equivalent in conventional concrete and KSMP concrete. Transportation, again in green, is the highest component for both of them. In fact, is actually almost the same. Conventional concrete and the KSMP concrete, the amount of cement is the same. We didn't replace the cement, we replaced the partially the aggregates with KSMP fibers. But totally, the KSMP concretes have a higher impact in terms of global warming. And that's due to the production of PET, the PET extrusion. If we look at the other way around, where we want to actually know what are the impacts, they are most impacted, sorry for the wording, in comparing conventional concrete and KSMP concrete, we can see that on the graph on the right-hand side, human toxicity and abiotic depletion are the impact categories. They are higher, and even new impact category that you don't have in the conventional concrete simply because you don't have the production of plastic. So that was our assessment, and you can see it's not that promising. We got a self-healing concrete. We actually know that self-healing concrete works, but we can't really sell that information we wouldn't convince in terms of sustainability of anyone. So we go back to our production, and we understand that in order to lower the KSMP concrete emission, what we need to look at is transportation, try to minimize the transportation, and try to understand how we can source raw materials locally. Replace the clinker, the Portland cement, with other sustainable option. What can we do about the PET production, the yellow one here? Is there any way I can minimize that? recycled plastic. Bear in mind though that whilst PT granulates, recycled PT granulates are available everywhere, their purity is not as good as virgin PT granulates, especially for the shape memory effect that the extrusion process gives to these fibers. So what we are doing now, thanks to the LCA, we are trying to go back to the lab and replace 30% of the PT granulates with recycled one and see whether we have the same shape memory effect that is able to close the crack. Also, this model is a cradle to gate analysis. And that kind of links with Esteban talk and David's question. If I were to do durability testing, if I know how to implement the service life into an LCA, if I know, for example, you said that the service life of one of those beams was 8 to 12 years. Yeah. So if I, yes. So if I have the information for my concrete and I can say the service life, I know that after 12 years I have to go back and replace some of the concrete or replace a concrete cover. If I have the information and I know with the self-healing concrete that doesn't happen, I can move then from a life cycle assessment cradle to gate to a cradle to grave, because I have information on the service life and the durability that will allow me to take into consideration that. So, current projects I'm working on and we at Cardiff are working on, obviously development of self-healing materials. We're using now LC3 cements. We're working a new plastic reinforcement to get rid of steel in concrete, as well as using mineral waste and waste foundry sand in concrete. And all of these projects, for each of these projects, we always do a life cycle assessment in parallel. Some of these projects, we didn't even start it yet. For example, the last one, Enhanced Carbon Negative Supplementary Cementitious Materials, is a collaboration with a company in Canada. We haven't even started the actual experiments because what we're doing at the moment with our students is doing a life cycle assessment first. Try to understand what's their process. It's not a earthquake, yeah? Try to understand what the process is for them and try to understand how we can minimize an environmental impact before even going to the lab. And just to say, because I'm very proud of that, one of the, obviously to understand the service life of any innovative material, any material that hasn't got any regulation with them, you need durability testing. You need to simulate what will happen to that structure in 100 years in terms to understand that. And we recently in Cardiff got this new lab, was funded by the Welsh government, which is, we call a time capsule, where you can simulate aging of any material, bonds, metals, plastic, and concrete, and infrastructure materials. And you can simultaneously simulate corrosion, UV exposure, wet and dry carbonation, along with freezing and thawing, along with mechanical loading. So it's like simultaneously you can get information about any aggressive environmental condition in weeks that could replicate the exposure to hundreds of years. Now, we got a few minutes. I'd like to have a volunteer to do a very basic life cycle assessment on the project. That would be cheating though. Yeah, okay. Yeah. you can come here, you can stay there. I just need to explain what is your project and try to break it down into processes.
So I'm working on repair motors. So that will be the end product. A motor which will have cement, sand, possibly capsules. So in terms of process, I think I will start with not with the cement extraction, but just with the cement, because I will probably take the cement from other companies.
Okay.
So my first will be transportation of the raw materials from the manufacturers, which will be cement and sand, to my batch mixing place where you have the big mixing machinery which is going to run. So that will be the first thing, will be the transportation, and then the mixing process, and putting them in bags. So that will also come in the production of the final bags, and then sending it to either contractors or the suppliers. So that will be my different processes.
Okay, and you understand how your supply chain works?
Yes.
So you know where you're getting the materials?
Yes.
Okay, and so that will be that's the start of a life cycle assessment. What's your name again?
Priya. Sorry.
What's Priya missed is she didn't say anything about the scope. What will you do a life cycle assessment for? And what's your functional unit of your repair mortar?
So first the scope. The scope would be manufacture and supply of repair motors to contractors for now. Functional unit would be, I think, CO2 emissions. I'm not sure. Yeah, I'll compare CO2 emissions.
No, and
Or
you know
energy.
why? You can't really compare your functional unit being also your impact category, because one of the impact category, one of your measure is the CO2 emission, the CO2 equivalent. So you can't have that as a
Okay, so I think it will be energy consumption or
energy consumption.
watts, like watt per hour or. No, but I will just supply. I'm not deploying the repair, but it's just supply. So my boundary is take the cement, put it in bags and supply the repair, and not the application itself. So would it be?
So perhaps the area that you're going could be actually
The volume.
the volume or the area. If I don't know much about your repair mortar, but
Yeah,
I guess
can be
it's
area or volume.
I guess your repair mortar might be obviously got something novel in that. So if you're comparing a repair mortar, a conventional one, and the Prius one, for the usage of that, I will probably go as Lai said, as a meter square.
So that will be the function unit. Okay.
That could be your function unit. Okay, anyone else wants to have a go? Think of this is an exercise to make you think of the processes of your life cycle assessment. And if you thought, obviously Davide did think very well on the service life, do you want to summarize your life cycle assessment as Priya did?
Yeah. Well, in my case, what I'm doing is to assess the environmental and economic sustainability, because I'm also interested in life cycle cost for the case of self-healing concrete. That means that I have to take into account for my analysis some of the self-healing products, agents that are added and are developed in the framework of SmartThings. So, well, actually, in my case, I tried to use an extended cradle to gate system boundary, because I took into account not only the production stage, but also the maintenance stages, but not the disposal ones, mainly because for the moment, at least for one case that I assessed, that is concrete containing superabsorbent polymers, because of the lack of standards for the disposal of concrete containing polymers, I wasn't able to predict how it has to be disposed. And I also assessed the case of UHPC containing a crystalline admixture. In that case, it was a cradle to grave or also a cradle to cradle, because in that case, for me, it was easier to estimate also the disposal stage. In both cases, the functional unit for me was a structure. Two same structure that had to fulfill the same function for the entire lifetime. For concrete containing superabsorbed polymers, it was a structure, it was a wall actually, that was made. I actually compared two walls. One of them contained less reinforcement because of the effects and improvements given by the superabsorbent polymers. And the other structure that I assessed for the case of UHPC was a water basin. And that was very interesting, I think, because we passed from a thickness of 40 centimeters for the case of ordinary Portland concrete up to 10 centimeters for the case of UHPC. So also to comment all together, I think that it's really interesting to discuss, to evaluate the production of 1 cubic meter. But for instance, my question about the project that you did present was, did you take into account any structural characteristic of that cubic meter? Because for instance, if the compressive strength of that is different in comparison to the ordinary Portland cement concrete, maybe we are not comparing two functional units that are able to fulfill the same function at the same time.
To answer that question, the compressive strength was the same. There was no significant variation between with or without fibers.
Okay. And well, another aspect that we have experienced for the moment is that, for instance, comparing an ordinary structure to the one containing superabsorbent polymers, it was possible more or less to reach the same environmental burdens, the same overall cost, sometimes with certain kind of improvements. But more than this experience that I have had until now during my PhD, for the case of UHPC, thanks to the structural properties of this material, it was possible to significantly reduce the thickness, and thanks to that we experienced not only a very improvement in terms of environmental sustainability, but also in terms of overall costs. So I mean, if we will combine, and this is what I'm trying to do at the moment, if we will combine the structural aspects together with the life cycle assessment aspects, that is basically durability assessment based design, there we will reach the goal of all of us developing a more sustainable world.
Yeah, correct. I think I mentioned that earlier when I started describing the LCA. We can't think of looking only at the environmental aspect and forgetting what the scope of the work is. So well said, Davide. We really need to keep that in mind and comparing like for like. Okay, to summarize, if you go back to Menti using the same code, can you see the question on yours? Oops. Ah, sorry. How many components an LCA must have at least? I told you there was a test at the end. Well done to those 7 who got there at the end. So 4 are the components of an LCA: goal and scope, lifecycle inventory, impact assessment, and interpretation. Next question. Okay, at the end we are going to reveal who those people are. But well done, Beyoncé. Question 2. What is the main regulation for LCA? No cheating, no Google. I expect at least one correct answer. Well done. Well done. Let's see if Beyoncé is still there. Well done, Lais. Final question. What type of analysis include the end of life of a product, process, or service? Careful on this one. 5 seconds left. Well done on cradle to grave. Someone got it wrong. Yes. The cradle to grave is the one that includes the end of life. But the cradle to cradle actually include also the beginning of life. So let's see who's got the most point in this one. Well done, Millie. Well okay, well done, Davide. So, how much do you know about LCA now? Ooh, we go on Esper now. Okay, maybe some from the audience online. Will you be using your LCA in your research? Maybe, okay. Getting there. At least there is no one in the third column. Yeah, if you got any question, I used also, if there is anyone online that wants to ask question, they can pop their question in the box.
I have one question more. I don't know if we do have time. Very rapid question. I suppose that you also use sometimes the environmental product declaration for the life cycle inventories. I don't know. Do you have any experience with the usage of them?
Yes and no. I'm working at the moment on a life cycle assessment of comparing supplementary cementitious materials in Europe and Japan. So the scope of that is to show how 50%, 60% replacement of Portland cement differs using GGBS fly ash in Japan and in Europe. My colleague in Japan, they are compiling the LCA, the lifecycle inventory, and they went back to the EPDs for super plasticizers and fly ash in Japan. Surprisingly enough, there was no entry in the lifecycle in the database, not even in EcoInvent. So I don't have any direct experience, if that's what you're asking, but I can ask them what was the process and how they entered that value into the...
Okay, because my question, but we can discuss later, is that most of the times the environmental product declaration, they don't include all of the 10 impact indicators. I don't know why. Maybe because it depends on the type of of the APD. So I was just asking how you did overcome this problem, but I think it's better to discuss later.
Yeah, we can discuss later. But as you said, the EPDs, they don't usually take into account all the impact categories. And for them, for whoever produces the EPD, it's, for example, it's really difficult to quantify human toxicity as opposed to other categories such as global warming, which is straightforward to calculate. But again, this back into your assumption, do you need to show or do you need to take into account human toxicity in your products? Any other question?
Can I still do it? Do we still have time for another question?
I think it's almost too late already, actually.
Oh, okay.
If you want lunch, maybe it's better to have a discussion than do it. Then we can ask what you're around for lunch, right?
Yeah.
Yeah, okay.
Okay.
Excuse me, Manuel